Hello everyone. Today I want to explain operation of a three-phase full converter in a simple way. Three-phase rectifiers provide high average output voltage compared to single-phase rectifiers. The ripple frequency in three-phase converter is more compared to single-phase converter. In case of single phase full converter, the ripple frequency is twice the supply frequency, whereas it is 6 times supply frequency in three phase full converter. The ripple in the load current can be reduced by connecting an inductor in series with the load. The ripple in the load voltage can be reduced by connecting a capacitor in parallel to the load. As the ripple frequency is more in case of three-phase converter, the size of the inductor and capacitor will be less. Coming to applications, three-phase converters are used in high-power DC drives, and two three-phase full converters connected in cascade, called as 12-pulse converter, is popularly used in HVDC transmission. Before going to three-phase full converter, I want to discuss basic concepts which are relevant to three-phase full converter. First of all, thyristor is a three-terminal device. Its terminals are anode, cathode, and gate. Whenever anode is positive with respect to cathode, thyristor is said to be in forward blocking mode and acts as a open switch. Whenever turn on is required, a small pulse is applied to gate and thyristor is switched into conduction and acts as a closed switch. Compared to diode, thyristor has a controlled turn on. Once thyristor is turned on and required power is transferred from source to load, thyristor can be turned off. There are two ways to turn off thyristor. The first one is when the thyristor current becomes zero, and the second method is when the thyristor is reverse biased. That means when anode is negative with respect to cathode, similar to diode. In this slide, thyristor is connected between two DC sources, V1 and V2. The anode as well as cathode are connected to positive terminals of V1 and V2. If anode is more positive with respect to cathode, thyristor is in forward blocking mode, and if gate pulse is applied and thyristor is switched into conduction. In this slide, there are three thyristors which are connected to three AC sources. Thyristor T1 is connected to A phase source, and T3 is connected to B phase, and T5 connected to C phase. A phase voltage is taken as a reference, given as Vm sin omega t. B phase lags A phase by 120, Vm sin omega t minus 120. C phase leads A phase by 120, Vm sin omega t plus 120. These are the waveforms of three phases. The voltage of A phase is positive between 0 to 180, and the voltage of B phase is positive between 120 and 300, and the voltage of C phase is positive between 240 and 420. So thyristor T1 can be turned on between 0 to 180, T3 can be turned on between 120 and 300, and T5 can be turned on 240 and 420. Redefining origin at 360 degrees, it is 60 degrees. Here, thyristor T1 is connected between two sources, A phase and C phase. Thus T3 is connected between B phase and A phase. Thus T5 between C phase and B phase. When T1 can be turned on, when T3 can be turned on, and when T5 can be turned on. If you look at the waveforms, till omega t equals to 30 degrees, the voltage of phase C is more positive. Hence, thyristor T1 is reverse biased. T1, the voltage of A phase is more positive from omega t equals to 30 degrees. Hence, T1 is turned on at 30 plus alpha. Similarly, T3, which is connected in B phase, the B phase voltage is more positive with respect to A phase from omega t equals to 150. So T3 is turned on at 150 plus alpha. Similarly, T5, which is connected in phase C, is turned on at 270 plus alpha. The circuit is a three-phase thyristor half converter, is also called as a positive group converter. There are three thyristors, T1 in A phase, T3 in B phase, and T5 in C phase. T1 is turned on at 30 plus alpha, T3 is turned on at 150 plus alpha, and T5 is turned on at 270 plus alpha. When T1 is turned on, T3 and T5 are in off state and load is subjected to A phase voltage. When T3 is turned on, the load is subjected to B phase voltage, and when T5 is turned on, the load is subjected to C phase voltage. These are output voltage and current for alpha equals to 30 degrees. When alpha equals to 30 degrees, T1 is turned on at 60 degrees, T3 is turned on at 180, and T5 is turned on at 300 degrees. When T1 is turned on at 60 degrees, the voltage suddenly rises from 0 to a particular value, and the voltage rises sinusoidally to peak value at 90 degrees and falls sinusoidally to 0 at 180 degrees. Here, initially the load is taken as resistive. As the load is resistive, the load current is in phase with the load voltage. At omega t equals to 180, the load voltage becomes 0 and the load current becomes 0. T1 is turned off. Ideally, T3 is turned on at 180, and from omega t equals to 180, the load is subjected to B phase voltage. At omega t equals 300, T3 is turned off and T5 is turned on. From omega t equals 300, T5 is on, the load is subjected to VCN. Here, when alpha equals 30 degrees, for every pulse, the load current falls to 0. Whenever the load current falls to 0, the load current is said to be discontinuous. In three-phase half converter, if alpha is greater than or equal to 30 degrees, the load current becomes discontinuous. For alpha less than 30 degrees, the load current is continuous even for resistive load. This is output voltage and current for alpha equals to 0. T1 is turned on at 30 degrees, T3 is turned on at 150, and T5 is turned on at 270. T1 is turned on at 30 degrees. The load is subjected to A phase voltage, and T3 is turned on at 150. And when T3 is turned on, immediately after 150, the voltage VAB is negative and T1 is turned off. And at omega t equals to 270, T5 is on. When T5 is on, T3 is off due to minus VBC. In continuous current case, turning on will turn off the existing thyristor. This is output voltage and current for alpha equals to 60 degrees, and it can be seen that the output current is discontinuous. For the same firing angle, the load inductance is increased to a sufficiently high value so that the load current is continuous. In this case, the load current oscillates around an average value of approximately 26.6 amps. Let's go to another circuit, and here thyristor T is connected to two negative sources. The anode as well as cathode are connected to negative terminals of sources V1 and V2. If cathode is more negative compared to anode, thyristor is said to be in forward blocking mode, and if gate pulse is applied, thyristor acts as switch. And in this slide, there are three thyristors, T2, T4 and T6. T2 is connected between phases C and B. T4 between A and C, and T6 between B and A. When T2 can be turned on, when T4 can be turned on, and when T6 can be turned on. If you look at the waveforms, the voltage of phase C is more negative from omega t equals to 90 degrees. So T2 is turned on at 90 plus alpha, T4 is turned on at 210 plus alpha, and the voltage of phase B is more negative from omega t equals to 330 degrees. So the thyristor T6, which is connected in B phase, is turned on at 330 plus alpha. This is another thyristor half converter, which is turned on in the negative half cycle of input voltage. So it is called as a negative group converter. T2 is connected in phase C, T4 in phase A, and T6 in phase B. Each thyristor is turned on when the respective phase voltages is more negative. T2 is turned on at 90 plus alpha, T4 is turned on at 210 plus alpha, and T6 is turned on at 330 plus alpha. When T2 is turned on, the voltage across load is VCN. When T4 is turned on, the voltage across load is VIN. And when T6 is turned on, the voltage across load is VBN. This is output voltage and current for alpha equals to 30 degrees. For alpha equals 30 degrees, T2 is turned on at 120, T4 is turned on at 240, and T6 is turned on at 360. This is output voltage and current for alpha equals to 0. T2 is turned on at 90, T4 is turned on at 210, and T6 is turned on at 330. The output voltages are identical for positive and negative group converters for the same firing angles. In three-phase half converter, there are two types. One is P group converter, which conducts only in the positive half cycle of input voltage, and N group converter, which conducts only in the negative half cycle of input voltage. In practice, half converter is not used, and if you draw the phase current, source current of each phase in half converter, there exists a DC component. It is essential that each phase should supply power in both half cycles of input voltage, and it can be achieved by using a three-phase full converter. This is the circuit diagram of three-phase full converter. P group converter and N group converter are connected in cascade, and T1 is turned on at 30 plus alpha, T3 is turned on at 150 plus alpha, T5 is turned on at 270 plus alpha, and the same way T2 in the N group, T2 is turned on at 90 plus alpha, T4 is turned on at 210 plus alpha, and T6 is turned on at 330 plus alpha. In three-phase full converter, for every 60 degrees, one thyristor is turned on, and each thyristor conducts for a duration of 120. And at any instant, two thyristors conduct, one from P group and one from one N group. Turning on one thyristor will turn off the existing thyristor in the same group if the load current is continuous. And this converter is also called as a 6-pulse converter, since there are 6 pulses in the output voltage for a period of 2 pi. Let us analyze the circuit operation by taking alpha equals to 30 degrees. And T1 is fired at 30 plus alpha. So for alpha equals to 30 degrees, T1 is turned on at 60 degrees. And let us assume that T6 is already in conduction. So from omega t equals to 60 degrees, T1 in the upper group and T6 in the lower group conduct, and T3, T5, T4 and T2 are in off state, and the current comes out from phases A and B and phase C in open circuit. So when T1 and T6 conduct, if you apply KVL, the voltage across load is VAB. The load is subjected to a line voltage of VAB. And T2 is turned on at 120. This is a phasor diagram, and the voltage of A phase is taken as a reference along positive y-axis. VBN lags A phase by 120, and VCN leads A phase by 120. The line voltage VAB leads A phase by 30 degrees, and its magnitude is √3 times phase voltage. This is A phase voltage, which is taken as a reference, and this is line voltage VAB, and compared to A phase, the line voltage leads phase voltage by 30 degrees. The voltage crosses 0 at minus 30 degrees. The line voltage reaches to peak value at 60 degrees, goes through 0 at 150. Similarly, again passes 0 at 330 degrees. For alpha equals to 30 degrees, T1, T6 are on during period 60 to 120. In the analysis of a three-phase full converter, or in drawing the output voltage, it is important to identify which part of the voltage is applied across the load. It is essential to identify which part of VAB is applied across the load. The remaining pulses are identical. And for alpha equals to 60 degrees, T1 and T6 conduct between 60 and 120. At omega t equals to 60, the line voltage is at peak value, and after omega t equals to 60 degrees, the voltage falls sinusoidally. And this highlighted portion is applied across load. Yeah, this is the output voltage. T1 is turned on at 60, T3 at T2 at 120, T3 180, T4 240, T5 300, and T6 360. And the load is RL, and you can see the load current oscillates around 92.5. Let us consider another case for alpha equals to 0. For alpha equals to 0, T1 is turned on at 30 degrees and T2 is turned on at 90 degrees. So during 30 and 90, T1, T6 conduct, the load is subjected to VAB. And at omega t equals to 30 degrees, the voltage, line voltage VAB, rise from omega t equals 30 degrees, the line voltage VAB rises sinusoidally, and at omega t equals to 60 degrees, it reaches peak, and after 60 degrees, it falls sinusoidally. So the highlighted portion is applied across load. This is output voltage and output current for inductive load. And finally, for alpha equals to 60 degrees, T1 is turned on at 90 degrees and T2 at 150. So during 90 and 150, T1 and T6 are on, and this portion is the highlighted portion is applied across the load. Is output voltage and current for alpha equals to 60 degrees. The next topic is expression for DC output voltage. For a period of 360 degrees from 30 plus alpha to 330 plus alpha, there are 6 identical pulses, and during 30 plus alpha to 90 plus alpha, T1, T6 are on, and the load voltage equals to VAB. The area under 6 voltage pulses can be given by this expression: 6 times integral pi by 6 plus alpha to pi by 2 plus alpha VAB d of omega t. The average DC voltage equals to area by time period, so 6 by 2 pi to this expression. And the final expression is 3 root 3 Vm by pi cos alpha. If firing angle alpha equals to 0, the DC output voltage equals to 3 root 3 Vm by pi, and if firing angle alpha equals to 90, VDC equals to 0. So for firing angle between 0 to 90, the output voltage VDC is positive, the output current is positive, the power flows from AC to DC. The converter is said to be in rectification mode. If firing angle is 180, the VDC equals to minus 3 root 3 Vm by pi, and again if firing angle equals to 90, the VDC equals to 0. So for the firing angle between 90 to 180, the output voltage VDC is negative and output current is positive. The power flows from DC to AC. The converter is said to be in inversion mode. So for the firing angle between 0 to 90, the converter acts as a rectifier, and for the firing angle between 90 to 180, the converter acts as an inverter. I want to discuss one application, HVDC transmission. By connecting 2 6-pulse converters in series with a phase shift of 30 degrees, a 12-pulse converter can be realized, which is popularly used in HVDC transmission. And at the sending end, the converter 1, which is a 12-pulse, is operated in a rectification mode with a firing angle between 0 to pi by 2, And at the receiving end, again, the same 12 pulse converter is operated in the inversion mode with a firing angle of pi by 2 and pi. This is how the power is transmitted in HVDC transmission. Thank you for watching the video. Good luck.